The universe began not with a gentle whisper, but with a firestorm of impossible scale. For a few fleeting microseconds, everything that exists was forged in a cauldron of pure energy. Today, we are not just observers of that ancient event, we have become its architects. By the end of this story, you will understand how physicists on Earth built machines that act as time machines, recreating the very first moments of everything. How did a structure smaller than an atom explode into the cosmos we see? What does a perfect, frictionless liquid have to do with your own existence? The answers lie in a realm where time and space themselves behaved differently. What does it feel like to hold a piece of the beginning of time in your hands? That initial state of unity is almost impossible to describe with our language of space and time. For a fleeting moment, all of reality was compressed into a volume so small it defies comprehension. A realm of pure potential where gravity, the force that shapes galaxies, was indistinguishable from the forces that hold atoms together. This was the Planck epoch, a frontier where our current rulebook of physics simply stops making sense. To even speak of it, we must accept that our familiar concepts of cause and effect, of here and there, may not have yet applied. It is the ultimate curtain drawn across the very first act of creation, but as the universe expanded, it also cooled, and in that cooling, structure began to emerge from the chaos. A critical transition occurred, one of the most profound phase changes in all of history. The single, unified superforce fractured, like a prism splitting white light into a spectrum of colors. Gravity peeled away, becoming its own distinct entity, and in that newly structured reality, the universe entered an era we can actually name and study, a state of matter so exotic it makes the core of the sun seem placid. This was the Quark-Gluon Plasma. Think of it not as a fire, but as a perfect primordial soup. In the world you and I inhabit, the fundamental building blocks of protons and neutrons called quarks are forever locked away. They are bound together by particles called gluons with such immense force that you can never isolate a single quark. But in the first microseconds after the beginning, the temperature and density were so astronomically high that this binding force was overcome. Quarks and gluons were not confined, they roamed freely in a searing, ultra-dense fluid. This was the universe's first structured state of matter, a swirling ocean of the most basic ingredients before they froze into the particles that would later build everything we see. This Quark-Gluon Plasma is the key. It represents the moment when the universe transitioned from an unknowable quantum state into something that follows rules we can begin to decipher. It is the oldest relic we can conceptually reach back and touch, the fingerprint of the cosmos just as it was starting to take a recognizable shape. To understand our own origins, we must understand this plasma. We must know its properties, its behavior, its very nature. But how do you study something that existed for mere microseconds over 13 billion years ago under conditions impossible to find anywhere in the present-day universe? The answer required not just a telescope but a time machine built here on Earth. Yet the term Big Bang itself can be a little misleading. It conjures an image of a single, localized explosion flinging matter out into empty space. But the reality is far stranger and more profound. The most pivotal events did not happen in the first few minutes or even the first few seconds. They happened in the first unimaginably tiny fractions of a second. This is the theory's finest hour, a period so brief it defies human intuition, yet it determined the fate of everything that followed. During this sliver of time, the universe did not just expand, it underwent a process called inflation. Think of it not as an explosion, but as a sudden, exponential stretching of the fabric of spacetime itself. For a fleeting moment, a region smaller than a proton was stretched to a size larger than our observable universe today, and it all happened faster than the speed of light. This is not matter moving through space, but space itself being created and stretching at a rate that seems to break all the rules. This inflationary burst had one crucial effect: it ironed out the wrinkles. Any tiny irregularities, any lumps or bumps in the early energy field, were stretched so immensely that the universe became remarkably smooth and flat on the largest scales. It was this act of cosmic smoothing that created the perfect, uniform canvas upon which all future structure could be painted. Without inflation, the universe might have remained a chaotic, crumpled mess, or collapsed back on itself almost immediately. This period set the initial conditions for everything: the eventual formation of the first atoms, the gravitational collapse into galaxies, and the vast web of clusters we see today. The mystery of what drove this inflation, what force could possibly cause spacetime to behave in such a dramatic way, is one of the deepest questions in cosmology. It is this very mystery, the need to understand the physics of that first fraction of a second, that fuels the ambition to recreate those conditions. We cannot build a machine that stretches spacetime itself, but we can aim for the next best thing. We can recreate the state of matter that existed immediately after inflation ended, when that stretched, smoothed universe was filled with the searing Quark-Gluon Plasma. By studying that plasma, we are looking for echoes of the inflationary moment itself, clues baked into the first structured matter about how the cosmic stage was set. Trillions of degrees is a number so large it loses all meaning. To even approach such a state, we must think not in terms of heat as we feel it, but in terms of pure, raw energy. In the first microsecond, the energy density of the universe was so immense that matter as we know it could not exist. Particles were not solid things, they were ephemeral excitations in a field of pure force, constantly popping into and out of existence. This is the domain of the Standard Model of particle physics, our most successful map of the fundamental forces and particles. It tells us that to unlock the conditions of the Quark-Gluon Plasma, we need to concentrate an almost inconceivable amount of energy into a space smaller than a single atom. Nature achieves this through the catastrophic collapse of a massive star, a supernova, but we cannot wait for a star to die nearby, nor can we control it. So we had to build our own controlled, microscopic star here on Earth. The tool for this is the particle accelerator, and its most powerful incarnation is the Large Hadron Collider. Buried deep beneath the border of France and Switzerland, this 17-mile ring is not just a machine, it is a vessel for recreating the past. Inside its superconducting tunnels, protons are accelerated to within a whisper of the speed of light, guided by immense magnets. They travel in opposite directions, completing over 11,000 laps every single second. When two beams are steered to collide head-on, the result is not a simple splash. For a vanishingly brief moment, in a volume 1,000,000 times smaller than a grain of sand, the energy of that collision becomes so intensely concentrated that it creates a fireball with a temperature over 100,000 times hotter than the core of our Sun. In that microscopic inferno, for less than a billionth of a second, the bonds holding quarks apart are shattered. The protons melt away, and for a fleeting instant, we have created a droplet of the primordial universe, a tiny speck of Quark-Gluon Plasma. It is an echo of the first microsecond, captured in a detector the size of a cathedral. But creating this speck of the ancient past is only the first miracle. The real challenge is that it vanishes almost before it exists. How do you study something that lives and dies in a timescale no camera can possibly capture? This is where our journey takes a tangible, almost miraculous turn. That microscopic fireball we create, that droplet of pure energy, does not behave like a gas or a simple explosion. It behaves as a liquid, not just any liquid, but the most perfect, frictionless liquid ever observed in nature. This is the Quark-Gluon Plasma, and its existence confirms a breathtaking chapter of our cosmic story. For those first few microseconds, the entire infant universe was not a cloud of hot gas. It was filled with this searing, soupy substance. Inside it, the fundamental building blocks of matter, the quarks, and the force-carrying particles that glue them together, called gluons, were set free. In your body right now, every proton in every atom is a prison for 3 quarks, held by gluons with a force so strong it is literally inescapable. But under the temperatures of the early universe, or inside our particle collisions, those prison walls melt away. Quarks and gluons cease to be individual inmates and instead become a collective, flowing entity. They move as one with a viscosity or thickness so low it approaches zero. It is a liquid with no internal friction, a substance that can flow around an obstacle without ever slowing down. This perfection is a direct signature of the extreme conditions, a telltale fingerprint of the universe in its infancy. By meticulously studying how this liquid expands and cools in our detectors, physicists are doing something extraordinary. They are reverse engineering the emergence of the rules that govern our reality. As this primordial soup cooled, the strong nuclear force, the very glue of existence, began to take hold. Quarks started finding partners, grouping into threes to form the first protons and neutrons. The free-flowing liquid froze into the first solid pieces of matter. So every time we recreate this plasma, we are watching the moment the cosmic blueprint was set, the instant the universe transitioned from a formless, energetic beginning into a state where structures, and eventually stars and planets and people, could even be possible. The discovery that we could create and measure this state stands as one of the great triumphs of modern science. It transformed a theoretical paragraph about the early universe into an observable, testable phenomenon in a laboratory. We are no longer just astronomers looking back at the light from ancient stars. We are archaeologists of time, sifting through the debris of a recreated past to understand the forces that built our world. But to witness that liquid universe, you need a camera capable of seeing the unseeable. The particle accelerator itself is just the engine, the device that creates the microscopic fireball. The true marvel, the eye of this time machine, is the detector that surrounds the collision point. These are not simple cameras, they are layered cathedrals of technology, each one a city block-sized monument to human curiosity. Take the ALICE detector at the Large Hadron Collider. Its name stands for a Large Ion Collider experiment, and its sole purpose is to study the Quark-Gluon Plasma. When 2 lead nuclei, stripped of their electrons, are accelerated and smashed together, they do not simply break apart, they momentarily melt, creating that droplet of primordial soup. The ALICE detector is built like a giant, nested onion, with each layer designed to catch a different type of evidence from the ensuing explosion. The inner layers track the paths of thousands of charged particles flying outward, while outer layers measure energy and identify different particle types. It must do all of this in the blink of a cosmic eye, because the fireball exists for only a yoctosecond. That is 1/trillionth of a trillionth of a second. A timescale so short it makes a nanosecond feel like an eternity. In that fleeting moment, the Quark-Gluon Plasma forms, expands, cools, and freezes back into a shower of ordinary particles that spray out in all directions. By meticulously reconstructing the paths and energies of every single piece of this debris, physicists perform a kind of cosmic forensics. They work backwards from the aftermath to deduce the properties of the original, vanished fireball. It is like studying the pattern of splinters from a shattered vase to determine the exact sound it made when it broke. Every collision is a unique event, a tiny, controlled little bang. And by analyzing millions upon millions of these collisions, the detectors like ALICE begin to build up a statistical picture. They reveal how the plasma flowed, how quickly it thermalized, and most importantly, they confirmed its astonishingly low viscosity. This data is our direct window into a state of matter that has not existed naturally since the universe was a mere few microseconds old. We are not just reading about the past in equations, we are touching it, one catastrophic collision at a time. The data from these collisions is a storm of chaos. From a single, vanishing droplet of primordial fire, thousands of new particles erupt and fly outward. To the untrained eye, it is pure noise, an indecipherable spray of subatomic shrapnel. This is the monumental challenge, observing something that not only vanishes in an instant but leaves behind a cryptic aftermath. The experiments built to solve this puzzle, like ALICE, ATLAS, and CMS at the Large Hadron Collider, are feats of engineering designed to detect the undetectable. They are not single instruments but entire ecosystems of technology, layered like a giant high-tech onion surrounding the collision point. Each layer has a specific mission. Some are precise trackers, mapping the curved paths of charged particles as they spiral through magnetic fields. Others are calorimeters, designed to stop particles in their tracks and absorb their entire energy, measuring it with exquisite precision. Still others are particle identification systems, acting like cosmic bouncers to determine exactly what type of particle is passing through. Every single one of the thousands of particles produced in a single collision leaves a tiny digital signature across these systems. The goal is to catch them all, to record every whisper of evidence from the fireball's explosive decay. This is where raw data transforms into profound understanding. Physicists are the ultimate cosmic detectives, sifting through this digital debris field. By meticulously analyzing the trajectories, they can trace particles backward to their point of origin. By summing the energies, they can calculate the immense temperature of the initial blast, but the most telling clues come from the patterns themselves. How do the particles flow? Is their distribution random, or does it show a preferred direction? It is within these subtle collective patterns that the ghost of the Quark-Gluon Plasma reveals itself. Imagine tossing a handful of pebbles into a still pond. The ripples they create will spread out in concentric circles. Now, if you toss those pebbles into a pond that already has a current, the ripples will be distorted, stretched along the direction of the flow. The particles from our collisions are like those ripples. By studying how their flow is distorted, physicists can measure the viscosity of the medium they traveled through, the Quark-Gluon Plasma itself. The discovery that this plasma flows as a nearly perfect liquid with almost zero internal friction was read directly from these patterns. This detective work turns a chaotic spray of data into a clear portrait of behavior, a snapshot of how matter behaved under the most extreme conditions imaginable. It showcases human ingenuity at its peak, building machines to recreate the past and developing the intellectual tools to interpret its faint, fleeting echoes. The perfection of that primordial liquid was not meant to last. As the universe continued its relentless expansion, it also cooled, and in that cooling lay the next great act of creation. The searing Quark-Gluon Plasma could not remain a free-flowing soup forever. Just as steam condenses into water droplets, this exotic state of matter had to transform. The force that governs the subatomic world, the strong nuclear force, began to reassert its dominance. The roaming quarks and gluons, which had enjoyed a brief moment of ultimate freedom, suddenly found themselves pulled back into confinement. This process is called hadronization, and it represents the moment the universe assembled its first permanent pieces. As the temperature plummeted below 2 trillion degrees, quarks began to find partners. Trios of quarks snapped together, bound by gluons, to form the very first protons and neutrons. These are the hadrons, the stable building blocks of atomic nuclei. In that critical microsecond, the raw ingredients of the cosmos froze into the architecture of everything we see. The stars, the planets, and every atom in your body can trace its lineage directly back to this sudden condensation from the primordial soup. Yet a profound mystery is woven into this transition. Did it happen smoothly, like butter slowly melting in a warm pan? Or was it a sudden, dramatic shift, more like water crystallizing instantly into ice? The answer holds the key to understanding one of the universe's greatest imbalances. For every particle of matter created in those early moments, theory suggests an equal particle of antimatter should have been created. Antimatter is matter's mirror twin, identical in mass but opposite in charge. When matter and antimatter meet, they annihilate each other in a flash of pure energy. If the universe had been perfectly symmetrical, all the newly formed protons would have met their antimatter counterparts and vanished. There would be nothing left but light. Yet here we are. Our very existence is proof that for every billion annihilations, one single particle of matter survived. Somehow, during that phase transition from plasma to protons, a tiny asymmetry was baked into the laws of physics. The precise nature of the transition, whether smooth or abrupt, could have amplified or suppressed that asymmetry. By recreating the Quark-Gluon Plasma and watching it freeze back into hadrons, physicists are searching for clues in that microscopic choreography. They are asking if the path matter took out of its primordial state left a faint trail, a preference for creation over annihilation that allowed a remnant of stuff to persist and build a world. This subtle preference for matter over antimatter is a clue to a deeper cosmic story, one written in the language of symmetry. In those first microseconds, the universe was not just a hot soup of particles, it was a place of profound and perfect symmetry. The forces that govern reality today were, in that unimaginable heat, merged into a single, unified entity. We live with four distinct forces: gravity, electromagnetism, the strong nuclear force that binds quarks, and the weak nuclear force behind radioactive decay. But rewind to the Quark-Gluon Plasma era, and the picture simplifies dramatically. In that searing inferno, two of these forces, electromagnetism and the weak nuclear force, were not separate at all. They were two facets of a single, elegant force called the electroweak force. In this state of perfect symmetry, particles like the electron had no mass whatsoever. They would have zipped around at the speed of light. But this perfect symmetry could not survive the universe's rapid cooling. As the temperature plummeted below a critical threshold, a cosmic phase transition occurred. Think of it like a magnet cooling. When a magnet is hot, its atoms are jumbled, and it has no north or south pole. It is perfectly symmetrical. But as it cools, its atoms align, choosing a specific orientation and breaking that symmetry. The magnet now has a distinct north and south. In the early universe, something analogous happened, but on a fundamental level. As it cooled, the unified electroweak force fractured. The symmetry broke. From that single force emerged the two distinct forces we know today, the familiar electromagnetic force and the more obscure weak nuclear force. This breaking of symmetry was not a silent event. It had a profound and tangible consequence. It gave mass to the universe. This is where the Higgs field enters the story. Imagine the entire universe filled with an invisible, treacle-like field. As the electroweak symmetry broke, this Higgs field switched on. Particles that interact strongly with this field, like the quarks that make up protons and the electrons that orbit atoms, suddenly began to slog through it, acquiring mass and slowing from light speed. Particles like photons, which do not interact with the field, remained massless and continue to zip through the cosmos at light speed. This mechanism, confirmed by the discovery of the Higgs boson at the Large Hadron Collider, explains why anything has substance at all. By recreating the energies of the early universe, our particle colliders are essentially turning back the clock to just before this symmetry breaking occurred. We are testing the very moment the rulebook of our reality was written, the instant the forces split and particles gained the heft to eventually form atoms, molecules, and us. This journey into symmetry is not just about verifying what we know, It is a search for cracks in the model. The standard model is breathtakingly successful, but it cannot explain everything like the overwhelming dominance of matter. Physicists hope that by pushing our recreations to even higher energies, closer to that first fraction of a second, we might glimpse the physics that operated when symmetries were even grander, when all forces were perhaps one. In this way, every collision is a probe into the architecture of existence itself, asking why our universe cooled into a state that allowed for complexity, for structure, and ultimately, for observers to wonder about it all. Our very existence is a cosmic anomaly. If the early universe truly began in a state of perfect symmetry, then every particle of matter forged in that primordial fire should have been matched by an equal and opposite particle of antimatter. Think of them as perfect mirror twins, identical in every way except for their opposite electrical charges. When matter and antimatter meet, they do not just cancel each other out, they annihilate completely, transforming their mass back into a burst of pure energy. In a perfectly balanced cosmos, this would have been the ultimate fate of everything. All the quarks and antiquarks, all the electrons and positrons, would have found their counterparts, embraced, and vanished into a sea of light. The universe would be a vast, empty expanse of radiation, with no stars, no planets, and certainly no one to wonder about it. Yet here we are, in a universe made almost entirely of matter. Every atom in every galaxy is a testament to a broken symmetry, a tiny but decisive tilt in the scales during those first microseconds. For every billion annihilations that took place, one single particle of matter was left behind. That one in a billion survivor is the reason for everything we see. This is the Matter-Antimatter Puzzle, and it is one of the most profound questions in all of science. Why is there something rather than nothing? The answer lies in a phenomenon with a technical but crucial name, CP violation. CP stands for charge and parity. In simple terms, it is a test of symmetry. If you take a particle and swap its charge for its antiparticle's charge, and then view its behavior in a mirror, the laws of physics should look the same. For a long time, physicists believed this symmetry was perfect, but experiments in the 1960s revealed a crack in the mirror. Certain rare particles, called kaons, decayed in a way that showed a slight preference for matter over antimatter. This was the first evidence that the universe has a built-in bias, a fundamental rule that treats matter and antimatter not as perfect equals, but with a subtle, one-sided favoritism. The challenge is that the amount of CP violation we have observed so far in particle decays is far too small to account for the overwhelming dominance of matter we see in the cosmos. It is like finding a single bent spoon in a factory that produces millions of perfectly straight ones, not enough to explain the skewed output. This tells us the real action, the major breaking of the symmetry, must have happened much earlier, under the extreme conditions of the Quark-Gluon Plasma. This is where our recreations become a direct search for our own origins. By smashing heavy nuclei together and creating that primordial soup, physicists are looking for any sign that quarks and antiquarks behaved differently as they swirled in that perfect liquid. Did they interact with the intense magnetic fields of the plasma in distinct ways? Did they freeze out into hadrons at slightly different rates? Any tiny discrepancy in their behavior could be the fingerprint of that initial cosmic tilt, magnified by the rapid expansion and cooling of the early universe. Solving this puzzle is not just an academic exercise, it is an existential one. It is the quest to understand the single most important accident in history, the flaw in perfection that allowed a material world to emerge from a symmetrical beginning. Every collision in our detectors is a replay of that critical moment, a chance to witness the delicate imbalance that made all the difference. That microscopic bias in the laboratory connects to the grandest picture of all, a photograph of the infant cosmos. While our particle colliders recreate fleeting moments of the first microseconds, the universe itself left us a permanent, panoramic snapshot from a slightly later chapter. This is the cosmic microwave background radiation, a faint glow that permeates every corner of space. To sense it, you would need eyes that see in microwave light, but its presence is the cooled remnant of the universe's fiery youth. It was emitted when the cosmos was about 380,000 years old, a toddler by cosmic standards. Before this moment, the universe was an opaque fog of charged particles and light, a plasma so dense that photons could not travel freely. They were constantly scattered, trapped in a brilliant, blinding haze. But as expansion drove the temperature down, a monumental change occurred. Electrons combined with protons to form the first neutral hydrogen atoms. Suddenly, the fog cleared. The universe became transparent, and that trapped light, last scattered from the searing plasma of that era, was finally set free to travel across the ages. That light, stretched and cooled by 13.8 billion years of expansion, is what we detect today as the cosmic microwave background. It is the oldest light we can see, a fossilized imprint of the universe at its moment of first clarity. But this snapshot is not a featureless white canvas. When scientists map it with exquisite precision, like the Planck satellite did, they see a mottled tapestry of tiny temperature variations. Some patches are ever so slightly warmer, others infinitesimally cooler. These minute fluctuations, mere millionths of a degree, are the most important wrinkles in the cosmos. They are the echoes of the quantum seeds planted during the inflationary burst in the very first fraction of a second. The microscopic quantum jitters that existed when the universe was smaller than an atom were stretched to astronomical scales by inflation, creating the slight over-densities and under-densities in the early plasma. These are the gravitational seeds from which everything grew. The slightly denser patches, revealed by the slightly warmer spots in the cosmic microwave background, had stronger gravity. Over eons, they pulled in more matter, eventually collapsing into the vast cosmic web of galaxies and galaxy clusters we observe today. Your existence, and the existence of every star in every galaxy, can be traced back to those specific tiny hotspots in this ancient light. This creates a powerful convergence of evidence. On one hand, we have the Quark-Gluon Plasma recreated in our accelerators, telling us about the physics of the first microsecond. On the other, we have the cosmic microwave background, a direct image of the universe 380,000 years later, showing us the consequences of that physics. Cosmologists now perform a profound cross-check. They use the laws of physics tested in particle colliders to run the cosmic film forward from the first microsecond. Their simulations predict how the quark-gluon plasma should evolve, how protons and neutrons should form, and how those initial quantum fluctuations should imprint themselves on the later cosmic microwave background. Then they compare that prediction with the actual, exquisitely detailed map of the sky. The match is stunningly precise. This agreement between the microscopic world of particle physics and the macroscopic story of cosmology is one of the greatest triumphs of modern science. It weaves a single, consistent narrative from the first unimaginable fraction of a second all the way to the structured universe we inhabit today. We are reading the same cosmic story written in two very different languages, the language of subatomic collisions and the language of ancient light, and they tell the same breathtaking tale of our origin. But these cosmic recreations are not confined to physical collisions alone. Alongside the immense detectors, another kind of time machine is running, one built not from steel and superconducting magnets, but from lines of code and raw processing power. This is the realm of the supercomputer, where the universe's first moments are simulated in breathtaking digital detail. While particle accelerators create a single, fleeting droplet of the primordial past, supercomputers can recreate entire oceans of it, running the experiment over and over with infinite variations. They use the mathematical framework of quantum chromodynamics, the theory that describes how quarks and gluons interact through the strong force. These equations are so complex that solving them for even a few particles interacting in the Quark-Gluon Plasma would take a human mathematician a lifetime. For a system of millions of particles, it is simply impossible without staggering computational muscle. That is where these digital behemoths come in. They divide the problem into billions of tiny pieces, calculating the interactions between virtual quarks and gluons as they swarm and collide in a simulated fireball. They track the entire life cycle from the initial violent impact through the formation of the perfect liquid to its eventual freeze out into a shower of hadrons. The result is not just an animation, it is a precise, quantitative prediction of what the detectors should observe. Physicists then take this virtual data and compare it pixel by pixel with the actual data from experiments like Alice. When the simulation matches reality, it validates our understanding of the underlying physics. When it does not, it points directly to something new, a crack in our theories where a deeper truth might be hiding. This digital playground allows for experiments that are impossible in the real world. What would happen if the strong nuclear force were 10% stronger? Would quarks still condense into protons, or would they form something entirely different? By tweaking these fundamental parameters in the simulation, researchers can explore alternate cosmic histories, testing the robustness of our universe's recipe. This synergy between physical experiment and digital simulation is what propels the field forward. The colliders provide the raw, messy data of reality. The supercomputers provide the clean, controlled testbed for interpretation. One asks the question of nature, the other helps us understand the answer. Together, they form a feedback loop, refining our models and guiding the next generation of accelerator experiments to ask even sharper questions. In this way, we are not just passively observing the past, we are actively learning its language, running countless digital rehearsals to ensure that when we finally recreate the cosmos in our labs, we know exactly what we are looking at. The discovery of this perfect liquid was a profound shock to the scientific community. When the first data from the collisions of heavy ions like gold and lead came in, physicists expected to see the signature of a hot, diffuse gas. The logic seemed sound. If you liberate particles from their bonds, they should fly apart freely, like steam from a boiling kettle. But the patterns in the detectors told a very different story. The particles emerging from the fireball were flowing together in a coordinated, collective motion, like a school of fish or a swirling eddy in a stream. This was the unmistakable fingerprint of a liquid, and not just any liquid. By measuring how this flow was distorted, researchers calculated its viscosity, its internal resistance to flow. The result was staggering. This Quark-Gluon Plasma had a viscosity so low it approached the absolute theoretical minimum allowed by the laws of quantum mechanics. It was, for all intents and purposes, a perfect fluid. This meant the early universe, in its first structured moments, was not a chaotic, billowing cloud. It was an astonishingly smooth and coherent substance, where the freed quarks and gluons interacted so strongly and so quickly that they achieved thermal equilibrium almost instantly, moving as a single, unified entity. This finding overturned textbook assumptions and forced a major rewrite of our models for extreme matter. It also created a fascinating and deeply unexpected bridge between the smallest and largest scales in physics. The mathematical description of this nearly perfect liquid's behavior bears a striking resemblance to equations used in two of the most esoteric areas of theoretical physics, string theory and black holes. This connection is known as the holographic principle. In its most daring form, it suggests that a three-dimensional volume of space, like our droplet of Quark-Gluon Plasma, can be completely described by information encoded on its two-dimensional boundary, like a hologram. Astoundingly, the physics of a certain type of black hole's event horizon, its two-dimensional surface, can be used to calculate properties like the viscosity of our four-dimensional primordial fluid. It is as if the universe is using the same mathematical blueprint for phenomena that could not seem more different: a black hole warping space-time and a droplet of the early cosmos. These unexpected links are more than just intellectual curiosities, they are guiding lights. They tell us that by mastering the physics of this ancient liquid, we might be glimpsing universal principles that govern all of reality under extreme conditions. Every new collision, every refined measurement of this liquid's flow, is not just a window into our past, it is a probe into the fundamental architecture of nature, suggesting that the secrets of the cosmos are written in the language of fluid dynamics. This unity between the vast and the minuscule is perhaps the most elegant truth revealed by our cosmic recreations. The story of the universe's first moments is not written in one language, but in two: a grand cosmological narrative and a precise quantum script, and they are translations of the same epic. When cosmologists look up at the cosmic microwave background, they are reading the final chapter of a book that particle physicists are writing from the first page in their underground detectors. The immense gravitational seeds for galaxies, visible as faint temperature variations in that ancient light, were born from quantum fluctuations so tiny they operated on a scale 1 billion times smaller than a proton. Those microscopic jitters, stretched to cosmic proportions by inflation, dictated where galaxy clusters would bloom billions of years later. This means the architecture of the entire observable universe, with its vast voids and glittering filaments of galaxies, was determined by laws that only reveal themselves when we smash subatomic particles together. The force that governs how quarks bind into a proton is the same force that, through gravity's accumulation, sculpted the Andromeda galaxy. It is a breathtaking continuum of cause and effect, where the rules of the quantum realm are the authors of the cosmic landscape. This is why the largest questions demand the smallest probes. To understand why the universe has the structure it does, we must understand the strong nuclear force. To decipher the matter-antimatter imbalance that allowed us to exist, we must hunt for CP violation in quark interactions. The fate of the cosmos is inextricably linked to the behavior of particles that lived for less than 1/1000th of a second. This synergy dissolves the artificial boundary between the science of the infinitely large and the science of the infinitely small. It reveals a single, coherent reality where the same fundamental principles manifest in wildly different ways depending on scale and energy. A physicist studying the flow of a perfect liquid in a particle collision and an astrophysicist modeling the evolution of the cosmic web are, in a profound sense, working on different facets of the same problem. Their tools are different. One uses a collider, the other a telescope, but their goal is identical: to trace the thread of physical law from the first microsecond to the present day. This holistic pursuit encourages a powerful shift in perspective. It shows us that the deepest mysteries are not isolated puzzles but interconnected pieces of a grand design. The quest to recreate the first microseconds is more than a technical achievement. It is a philosophical journey that reaffirms our place in a rational, comprehensible universe. By peering into the quantum forge where everything began, we are not just learning about the past, we are reading the fundamental signature of reality itself, a signature written equally in the spin of a quark and the spin of a galaxy. The perfection of our laboratory recreations, however, comes with inherent and humbling constraints. We are not building a full-scale model of the infant cosmos. We are creating a fleeting echo, a microscopic sample of its conditions. The fireball produced in a particle collision is unimaginably tiny and exists for a vanishingly short time, a mere yoctosecond. In contrast, the Quark-Gluon Plasma that filled the entire early universe was a vast, homogeneous sea that persisted for several crucial microseconds. This difference in scale and duration is not a minor detail. it shapes the very phenomena we can study. Our tiny droplets give us a snapshot of the local physics, the behavior of the soup in one small region. But the universe-wide plasma had time for large-scale currents and waves to develop, processes we can only infer indirectly through our simulations. Furthermore, there is a fundamental energy frontier we simply cannot cross with today's technology. The Large Hadron Collider operates at energies of trillions of electron volts, which is enough to melt protons into quark-gluon plasma and even glimpse the electroweak symmetry breaking. But to probe the very first instance, the hypothesized grand unification epoch where the strong, weak, and electromagnetic forces were one, we would need energies a trillion times higher. That realm remains for now firmly in the domain of theory. These limitations are not failures, they are the signposts of an active and honest science. They define the boundary between what we can test and what we must still dream of. They are the very reason plans are already being drawn for next-generation colliders, machines that would be more powerful and precise, and for novel detection techniques that could capture even fainter signals from our artificial fireballs. Every unanswered question, every gap between our model and the data, is not an end but a beginning. It is a challenge whispered from the first microsecond, urging us to build better time machines, to look deeper, and to refine our understanding of that magnificent and mysterious dawn. Our current cosmic rulebook, the Standard Model, is a masterpiece of prediction and precision. It tells us how quarks form protons, how particles gain mass from the Higgs field, and how forces like electromagnetism operate. It successfully describes the physics of the quark-gluon plasma we recreate and explains the universe's behavior from that first microsecond onward. Yet, for all its triumphs, this rulebook is incomplete. It contains glaring blank pages where some of the universe's most profound mysteries reside. The Standard Model does not incorporate gravity, the very force that shapes the cosmos on the largest scales. It offers no candidate for dark matter, the invisible substance that outweighs all visible stars and galaxies 5-to-1. And as we saw, it cannot fully account for the overwhelming dominance of matter that allows our existence. These are not small footnotes, they are fundamental features of reality that our best theory simply cannot explain. This tells us that the Standard Model, as brilliant as it is not the final word. It is an approximation, a set of rules that work beautifully for the universe as it cooled, but perhaps not for the universe in its very first, most extreme state. To fill those blank pages, physicists propose theoretical frameworks that go beyond the Standard Model. These are not wild guesses, but mathematically rigorous extensions of our current understanding. One prominent idea is supersymmetry. This theory proposes that every known particle has a hidden superpartner twin. The electron would have a selectron, the quark would have a squark. These superpartners would have been abundant and active in the high-energy chaos of the first microsecond, influencing how the primordial plasma behaved and cooled. Another mind-bending proposal involves extra dimensions of space beyond the three we experience. In these theories, gravity appears weak to us because it is diluted, leaking into these hidden dimensions. In the ultra-dense early universe, these extra dimensions could have been compact but significant, altering the dynamics of the cosmic fireball in detectable ways. This is where our recreations transform from confirmatory experiments into voyages of pure exploration. When we collide particles at these incredible energies, we are not just testing the Standard Model's predictions, we are actively searching for any anomaly, any tiny deviation from what is expected. Does the quark-gluon plasma cool a fraction faster than our simulations predict? Does the spray of particles show an odd pattern that cannot be explained by known forces? Such a discrepancy would be monumental. It would be a crack in the foundation, a signal that something new is at play, a particle or a force that was present at the dawn of time but has since faded from view in our cooler, calmer cosmos. Every single collision in detectors like ATLAS and CMS is therefore a dual-purpose event. It confirms our stunningly successful picture of the early universe, and simultaneously, it scans the debris for the unexpected flicker that could point to a deeper truth. We are using the conditions of the first microsecond as a filter, a high-energy sieve designed to catch phenomena that simply do not manifest under ordinary circumstances. In this light, our particle accelerators are the most sensitive probes for physics we have not yet dreamed of, machines that ask the universe a direct question: what were you truly like in your very first breath? The answer may lie not in what we find, but in what we find that does not fit. The profound questions we ask about our origins do more than just advance science. They ignite the imagination of those who will shape its future. This dramatic narrative of recreating the cosmos in a laboratory has a unique power to inspire. It transforms abstract equations and complex theories into a tangible, epic story of discovery, one that resonates far beyond the walls of research institutions. For a young student, the idea that scientists can generate a substance older than the stars is not just a fact, it is a spark. It makes the scientific method come alive as a thrilling detective story, beginning with a bold theoretical prediction about the early universe and culminating in its stunning experimental verification inside a machine like the Large Hadron Collider. This journey from hypothesis to proof is the very heartbeat of science, demonstrated on the grandest possible stage. Major research centers like CERN have harnessed this captivating power through extensive outreach programs. They open their digital doors to classrooms around the world, offering virtual tours of the colossal detectors and connecting students directly with the researchers who operate them. These initiatives demystify the process, showing that the people asking these monumental questions are not distant figures in lab coats, but curious individuals driven by the same sense of wonder. By presenting the quest to understand the first microseconds as a great human adventure, these programs make careers in science, technology, engineering, and mathematics feel accessible and deeply meaningful. They show that STEM fields are not just about memorizing formulas, but about solving the greatest mysteries of existence. This area of physics makes the intangible tangible. It takes a concept as vast as the Big Bang and allows us to hold a piece of its evidence conceptually in our hands through the data from a collision. This act of cosmic archaeology fosters a specific kind of awe, one rooted in understanding rather than mystery. It encourages critical thinking by inviting everyone to follow the evidence, to see how each puzzle piece from detectors and simulations fits together to form a coherent picture of our past. Ultimately, this pursuit reminds us that the drive to comprehend where we come from is a fundamental part of being human. It is a story that belongs to everyone, a continuous thread of curiosity that connects the first questions ever asked around an ancient fire to the experiments running today deep underground. By sharing this story, we do more than educate. We pass on a torch, inviting a new generation to look at the night sky and not just see points of light, but to see a history written in the language of quarks and gluons, a history they are now empowered to help read. This immense power to recreate cosmic beginnings is not without its own gravity, a weight of responsibility that extends far beyond the laboratory. When we manipulate conditions that mimic the universe's creation, we step into a role that is as much philosophical as it is scientific. We are not just observers of nature, we are now active participants, coaxing its deepest secrets from the void. This reflects a fundamental human desire, a need to comprehend our origins and, by extension, our place in the vast cosmic story. With this profound knowledge comes an equally profound ethical responsibility. The same principles that allow us to understand the strong nuclear force could, in different hands, be applied to technologies with immense destructive potential. The global scientific community engaged in this work operates under a shared understanding that the pursuit of fundamental knowledge must be coupled with a commitment to peace and the betterment of humanity. This is why collaborations like those at CERN are built on open international partnerships, with research published freely for all to see, ensuring that the light of discovery illuminates the path for everyone, not just a privileged few. The scale of these endeavors naturally prompts reflection on priorities. Constructing a 17-mile particle accelerator or a detector the size of a building represents an investment of resources, intellect, and global cooperation on a staggering scale. It is valid to ask, in a world facing immediate challenges, why we should devote so much to studying the first microsecond of time. The answer lies in the very nature of curiosity-driven science. History shows us that exploring the most fundamental questions of existence often yields unexpected, transformative benefits for society. The World Wide Web was invented at CERN to help physicists share data, a tool that now connects the planet. Advances in superconductivity, computing, and medical imaging like PET scans have all flowed directly from the technological frontiers pushed by particle physics. The pursuit of understanding our cosmic origin is a catalyst for innovation that ripples through our entire technological civilization. More than that, it fulfills a deep human need for meaning. To know that we can trace the lineage of every atom in our bodies back to a searing droplet of primordial liquid is to feel a connection to the cosmos that is both humbling and empowering. These experiments represent a shared human project, a testament to what we can achieve when we collaborate across borders, driven not by profit or power, but by a collective wonder about where we came from. Engaging with these broader implications does not distract from the science, it completes it. It connects the technical triumph of detecting a perfect fluid to the timeless human reflections on existence, curiosity, and our enduring drive to explore. In this light, every collision is more than data. It is a statement about who we are, a species that can look back 13.8 billion years and dare to ask, how did this all begin? The boundaries of our current time machines are not the end of the story, they are merely the prologue. To peer even deeper into that first microsecond, to approach the very moment of cosmic inflation, we must build new machines of even greater ambition. The blueprints are already on the drawing board, representing the next great leap in our quest to witness creation. One such vision is the future circular collider. Imagine a new tunnel buried deep underground, not 17 miles in circumference, but a staggering 56 miles long, forming a ring that could encircle a major city. Within it, particles will be accelerated to energies 7 times greater than what the Large Hadron Collider achieves today. This immense power would allow us to create Quark-Gluon Plasma fireballs that are hotter, larger, and longer-lived, giving us a far clearer and more detailed portrait of that perfect liquid. We could study its transition into matter with unprecedented precision, hunting for the subtle signatures of CP violation that might finally explain our universe's matter dominance. Another machine, the Electron-Ion Collider, takes a different but equally crucial approach. Instead of smashing protons or heavy ions together, it would fire precise beams of electrons into protons or atomic nuclei. Think of the difference between crashing 2 cars together to see what spills out, versus using an incredibly high-powered scanner to peer inside a single, stationary engine. The Electron-Ion Collider would act as that scanner, using electrons as a clean probe to map the internal structure of protons and the way gluons themselves interact within the Quark-Gluon Plasma. It would let us see how the strong force distributes itself at extreme energies, offering a fundamental new perspective on the glue that holds reality together. These are not just incremental upgrades, they are transformative instruments designed to explore territories of energy and time we have never before accessed. They promise to push our recreations from a few microseconds after the beginning to a fraction of that, perhaps even brushing against the physics that drove cosmic inflation itself. The scale of such projects is by necessity global. No single nation could or should undertake them alone. They require a symphony of international collaboration, uniting thousands of scientists, engineers, and technicians across continents, all sharing data, expertise, and a common goal. This collective endeavor is a powerful testament to science as a unifying human language, a shared project that transcends borders in the pursuit of universal understanding. The decision to build them is a statement about our values, a commitment to investing in pure curiosity and the long-term future of knowledge. What might we find in that deeper past? Perhaps we will discover particles predicted by theories like supersymmetry, hiding in the debris of these more violent collisions. Maybe we will witness a phase transition so dramatic it reshapes our entire narrative of the early cosmos. Or we could encounter something entirely unforeseen, a phenomenon that forces us to rewrite the cosmic rulebook from its very first line. These future colliders are our invitations to that unknown dawn, machines that will let us listen more closely to the echo of the beginning and finally understand the whisper that started it all. The journey from that primordial fireball to the stars is a direct line. The same Quark-Gluon Plasma we recreate for a Microsecond in our detectors might not have vanished entirely from the cosmos. It could exist today, frozen into an unimaginably dense state at the heart of the universe's most extreme objects, neutron stars. When a massive star ends its life in a supernova, its core can collapse into a city-sized sphere of such incredible density that a single teaspoon of its material would weigh as much as a mountain. Under that immense gravitational pressure, the protons and neutrons at the star's very center may themselves be crushed, breaking down into their constituent quarks. This would create a permanent, super-dense core of quark matter, a cold, compressed cousin of the hot, expanding plasma from the beginning of time. It is a staggering thought that a substance we fleetingly create on Earth might be locked in the hearts of distant stellar ghosts. This is where the connection between nuclear physics and astrophysics becomes beautifully concrete. The equations that describe how quarks and gluons interact in our laboratory plasma are the very same equations astrophysicists use to model the interior of a neutron star. By measuring the properties of our artificial fireball, its pressure, its viscosity, its equation of state, we provide critical data points for these cosmic models. We are essentially performing a laboratory experiment that informs our understanding of an object thousands of light years away. This cross-pollination solves real puzzles. For instance, the maximum possible mass of a neutron star is a direct consequence of the strength of the forces inside it. If the core transitions to quark matter, it changes how the star resists further gravitational collapse. Our accelerator data helps constrain these possibilities, telling astrophysicists what kinds of interiors are physically plausible. This synergy exemplifies a profound truth about science, that the deepest questions are rarely confined to one discipline. A discovery in a particle detector beneath the Alps can directly illuminate the nature of a dense stellar remnant, forging a link between the smallest scales and some of the largest, most dramatic objects in the universe. It demonstrates that fundamental research, driven by pure curiosity about our origins, often becomes the key that unlocks mysteries we had not even fully anticipated. The sheer power of these experiments can sometimes lead to a dramatic but mistaken idea. You might have heard sensational headlines warning that scientists are trying to create a new Big Bang in a laboratory, or worse, a black hole that could swallow the Earth. These stories capture the imagination, but they fundamentally misunderstand the scale and purpose of the work. What physicists are actually doing is far more precise and far less apocalyptic. They are not creating a universe from nothing. They are recreating, with exquisite control, the specific conditions of temperature and density that existed in a tiny, fleeting region of the early cosmos. Think of it not as staging the entire opening act of a play, but as reconstructing a single, crucial line of dialogue in a soundproof booth to study how the actor's voice would have sounded. The fireball in a detector is a microscopic speck, a droplet of energy that vanishes almost before it exists, governed entirely by the known laws of physics. It poses no threat because its energy, while incredibly concentrated, is minuscule in absolute terms. The goal is insight, not genesis. This leads to another important clarification about what we can truly see. We are not and cannot directly observe the exact moment of creation itself. That first fraction of a second remains shrouded behind the curtain of the Planck epoch, a realm where our current physics breaks down. Instead, we are master detectives of the aftermath. We create that microscopic fireball, the Quark-Gluon Plasma, and then we study the debris it leaves behind as it cools and freezes. We analyze the patterns in the thousands of particles that spray out, and from that forensic evidence, we infer the properties and behavior of the original, vanished state. It is like hearing a distant echo in a canyon and using the sound to map the shape of the cliffs that produced it. We are not witnessing the Big Bang. We are listening intently to its very first reverberations, the echoes that have traveled across 13.8 billion years to reach our instruments. Setting the record straight on these points is not about diminishing the wonder of the science, but about grounding it in its true, staggering reality. The real story is awe-inspiring enough without needing fictional peril. By understanding that these are controlled, safe, and profoundly insightful experiments, we can appreciate them for what they are, humanity's most ambitious attempt to hold a piece of the cosmic dawn in our hands, to run tests on it, and to ask it direct questions about our own existence. This clarity ensures that public fascination is directed toward the genuine marvel of discovery, rather than being sidetracked by unfounded fears or pseudoscientific claims. It allows the science to speak for itself, revealing a universe that is not only vast and ancient but also, in its fundamental laws, remarkably accessible to our curiosity. There is a profound beauty written into the mathematics of creation. For the physicists who spend their lives studying the first microseconds, the equations are not just tools, they are works of art. The theories that describe the unified forces and the quark-gluon plasma possess an elegance that many researchers describe as deeply compelling, a kind of mathematical harmony that feels true. This aesthetic sense is far more than a poetic flourish. It has been a reliable guide through the history of science. Time and again, the universe has shown a preference for simple, symmetrical, and elegant explanations over convoluted ones. The drive to recreate those initial moments is fueled by this search for underlying order, a belief that behind the apparent chaos of a particle collision lies a structure of breathtaking coherence. It is a quest to witness the cosmic blueprint not just as a set of instructions, but as a masterpiece of logic. This perspective transforms the entire endeavor. The massive detectors and intricate simulations become more than instruments. They are the brushes and chisels we use to trace the contours of a fundamental beauty that existed before stars or planets. When data from a collision matches a prediction born from an elegant equation, it feels like a moment of recognition, as if we have finally heard a note from a symphony that has been playing since the beginning of time. This connection bridges the technical and the human, reminding us that science at its frontier is a deeply creative act. It shares the same impulse that drives an artist or a composer, a desire to find and express profound patterns in the nature of reality. To appreciate this is to understand why someone would devote a lifetime to studying a fluid that lasts less than a blink. They are not just collecting data, they are learning to see the universe through the lens of its own inherent grace, discovering that within the furnace of the beginning, there was also a sublime and silent order. Every culture has told a story of how everything began, from the cosmic egg of ancient Chinese myth to the primordial waters of Babylonian legend, from the dreamtime of Aboriginal Australians to the great tree Yggdrasil of Norse cosmology. Humanity has always looked to the sky and asked the same fundamental question. Where did all of this come from? These creation myths provided meaning, order, and a place for people within a vast and often mysterious universe. They were the first cosmologies, born from observation, wonder, and the deep need to understand our place in the grand scheme. Today, we tell a different kind of origin story, one written not in allegory but in algebra, not in poetry but in particle data. Yet the impulse is precisely the same. The scientist peering into a detector at CERN and the ancient storyteller gazing at the stars are driven by an identical, timeless curiosity. We are still seeking our origin, still trying to read the opening lines of our cosmic biography. What has changed is not the question but the method. We have traded revelation for experimentation, faith for falsifiable evidence. Our new creation myth is built not on tradition, but on a foundation of repeatable observation, mathematical prediction, and relentless peer review. It is a story that welcomes challenge and evolves with every new piece of data. This empirical approach is what makes the scientific narrative uniquely powerful. It offers a description of reality that is provisional, self-correcting, and astonishingly precise. When we collide lead nuclei to create a droplet of Quark-Gluon Plasma, we are performing a ritual of a new kind, a ceremony of verification. We are asking the universe to show us its birth certificate, and it is answering in the language of subatomic debris. The parallels between ancient myths and modern cosmology, however, run deeper than mere shared curiosity. Many myths speak of a beginning from a formless unity, a chaos or void that gives rise to order and structure. The scientific account echoes this profoundly. Our story also begins with an undifferentiated state, a singularity of pure energy where all forces were one, which then differentiated through symmetry breaking, giving rise to the distinct particles and forces that built our world. Both narratives grapple with the ultimate mystery of something emerging from what seems like nothing. Recognizing this shared thematic ground does not diminish the scientific account, it elevates it. It places our modern quest within the grand, sweeping arc of human intellectual history. It shows that the drive to recreate the first microseconds is not a cold, technical exercise, but the latest expression of a fundamental human yearning. We are using the most advanced tools ever devised to satisfy the oldest longing we possess. This context adds a rich layer of meaning to the data streaming from our detectors. Every graph and simulation is more than information. It is a verse in an epic poem we are composing together, a poem about where we came from and, by extension, who we are. By understanding this lineage, we see that the search for our cosmic origin is one of the most human endeavors imaginable, connecting the cave painter to the physicist across millennia, all united by a single, beautiful question whispered into the darkness of time. The equations that map the cosmos also chart a path toward healing. Those immense particle accelerators and cathedral-sized detectors are not just time machines, they are also engines of innovation, demanding technological leaps that inevitably spill over into our daily lives. The quest to see the first microsecond has, time and again, solved problems we did not yet know we had, gifting us tools that transform medicine, computing, and communication. Consider the precise targeting required to steer two beams of protons into a head-on collision. That same beam control technology is the foundation for modern proton therapy, a form of cancer treatment. Unlike conventional radiation, which can damage healthy tissue on its path to a tumor, proton beams can be tuned to deposit their maximum energy at a very specific depth, precisely where the cancerous cells reside. This minimizes collateral damage to surrounding organs, offering a more focused and often gentler treatment option. The development of these systems was directly propelled by the needs of high-energy physics, where controlling particle beams with nanometer precision is not a luxury, it is the entire experiment. Then there are the detectors themselves. To capture the fleeting spray of particles from a quark-gluon plasma, scientists had to invent new ways of seeing. One such innovation is the Metapix chip, a radiation-detecting sensor so precise it can track individual particles, much like a digital camera counts individual photons of light. Originally developed to improve particle tracking at CERN, this technology has been adapted into surgical imaging tools. Surgeons can now use handheld scanners equipped with Metapix during operations to see exactly where radioactive tracers have accumulated in a patient's body, providing real-time, high-definition maps of tumors or sentinel lymph nodes. This turns what was once a blurry statistical image into a sharp, actionable picture, directly guiding a surgeon's hand with unprecedented clarity. The detector built to find elusive quarks now helps find elusive disease. Perhaps the most famous and ubiquitous spin-off is the World Wide Web. Born at CERN in the late 1980s, it was created to solve a very specific problem. How could thousands of physicists scattered across the globe easily share and access the immense volumes of data and complex software generated by their experiments? Tim Berners-Lee's proposal for a system of hyperlinked information was the elegant answer. This tool for scientific collaboration escaped the laboratory and rewired human civilization, creating a new paradigm for communication, commerce, and access to information. It is a profound reminder that infrastructure built for sharing knowledge about the universe can become the infrastructure for sharing all knowledge. Beyond the web, the sheer computational challenge of processing data from millions of collisions drove advances in distributed computing. The grid computing models pioneered to handle this deluge now underpin cloud services and large-scale data analysis in fields from genomics to financial modeling. Even the pursuit of the coldest temperatures on Earth, required to create the powerful superconducting magnets that steer particle beams, has yielded practical rewards. The technology for cooling and maintaining miles of superconducting cable at temperatures colder than deep space has accelerated the development of magnetic resonance imaging, or MRI. The powerful, stable magnetic fields at the heart of every hospital MRI scanner rely on the same principles of superconductivity perfected for particle accelerators. This non-invasive window into the human body, which reveals soft tissue detail no X-ray can match, is a direct descendant of the technology built to peer into the heart of matter. These are not happy accidents, they are the inevitable fruits of working at the absolute frontier of engineering. When you push to create the hottest temperatures, you must also master the coldest. When you need to process the world's largest datasets, you invent new ways to distribute computation. When you require perfect precision to see the invisible, you create tools that redefine vision itself. This feedback loop between fundamental questions and practical solutions is a powerful argument for the value of curiosity-driven science. The substantial investment in these massive experiments is not a diversion of resources, but a multiplier. It seeds entire industries, trains generations of engineers and problem solvers, and delivers technologies that return the investment many times over in improved health, economic growth, and connectedness. The story of the first microsecond, therefore, is not locked away in a physics journal. It is written in the quiet hum of an MRI scanner, the global reach of a web page, and the targeted beam that offers hope in a fight against illness. By seeking to understand the origin of everything, we repeatedly discover new ways to improve the human experience. This global pursuit of the first microsecond is built on a foundation of shared purpose. The machines that recreate our cosmic dawn are not owned by any single nation. They are monuments to a collective human endeavor. The Large Hadron Collider alone involves thousands of scientists, engineers, and technicians from over 100 countries, representing a mosaic of cultures, languages, and political systems. Yet within the tunnels and control rooms, those distinctions dissolve in the face of a common question. This collaboration stands as a powerful testament to the unifying force of pure curiosity, proving that the desire to understand our origins can bridge divides that seem insurmountable elsewhere. It provides a tangible model for how humanity can approach its grandest challenges, from climate research to space exploration, demonstrating that diverse teams united by a shared goal can achieve what would be impossible in isolation. The entire structure of this work relies on principles that are both simple and radical: open data sharing, rigorous peer review, and a foundational commitment to empirical truth. Every finding, every dataset from a collision, is published for the global community to scrutinize, test, and build upon. This transparency ensures that the knowledge generated belongs to everyone, advancing our collective understanding at a pace no closed system could match. In a world often fractured by conflict, these vast scientific partnerships offer an inspiring counter-narrative, a quiet proof that cooperation on a planetary scale is not only possible but profoundly successful. They remind us that the questions written in the fabric of the cosmos do not recognize borders, and neither should the quest for their answers. The story of the first microsecond is told not only by data, but by the people who listen for its echo. Behind every graph and simulation are individuals who have dedicated their lives to a single, profound question. Take, for instance, a young graduate student staring at a screen in a control room deep underground. For weeks, she has been monitoring collisions, watching the chaotic spray of data scroll by. The models predict a certain pattern in how particles flow from the Quark-Gluon Plasma, but something in the numbers looks subtly off. It is not a dramatic error, just a quiet, persistent discrepancy that nags at her. She brings it to her team, and together they spend months checking the calibration of the detector, rerunning simulations, and debating interpretations. There are late nights fueled by coffee and collaboration, moments of frustration when a promising lead dissolves into a software glitch, and the quiet perseverance of returning to the problem day after day. This is the unglamorous, essential heart of scientific discovery. Then, one day, after a particularly long analysis, a new plot appears on her screen. The data finally aligns, not with the old expectation, but with a refined model that accounts for a previously overlooked interaction. In that moment, the discrepancy transforms from a problem into a discovery, a tiny but real step forward in mapping the behavior of the primordial fluid. That exhilaration, the sudden clarity after so much focused work, is a feeling shared by researchers across the globe working on these experiments. Another physicist might recall the intense camaraderie during the construction of a detector component, a project that required engineers, technicians, and theorists to solve problems no textbook had answers for. They remember the shared triumph when a complex system finally came online, not as a victory for one person, but for an entire international collaboration. These personal stories reveal science as it truly is, a deeply human endeavor built on a foundation of patience, teamwork, and resilient curiosity. It is a process punctuated by far more failed hypotheses than celebrated breakthroughs, where progress is often measured in millimeters over years. By sharing these narratives, we see that the cosmic time machine is not an autonomous entity. It is the collective work of thousands of hands and minds. Each researcher brings their own unique perspective, their own moment of wonder that first drew them to ask how the universe began. One might have been captivated by the night sky as a child, another by the elegant symmetry of an equation. Their personal journeys, with all their challenges and small victories, weave the emotional texture into the intellectual tapestry of the quest. This reminder is vital. It grounds our grand cosmic story in the relatable experiences of determination and shared purpose. When we learn about the Quark-Gluon Plasma, we are also learning about the people who dared to recreate it, individuals who chose to spend their lives listening for the faintest whisper from the dawn of time. Their stories assure us that the greatest mysteries are approached not by lone geniuses in isolation, but by communities of passionate explorers, each contributing a single note to a symphony of understanding that spans the entire world. This relentless pursuit thrives on a beautiful paradox. The most powerful scientific minds are not those who claim to have all the answers, but those who are most comfortable living with profound questions. The entire quest to recreate the first microseconds is built upon a foundation of acknowledged uncertainty. Scientists do not approach the particle detector with a completed textbook in hand. They arrive with a map that is mostly blank, its edges fading into terra incognita. The gaps in that map, the places where their equations go quiet or their predictions falter, are not failures. They are the most exciting places of all. They are the signposts pointing toward the next frontier, the motivation to build a more powerful collider, design a more sensitive detector, or conceive a more elegant theory. This embrace of the unknown is the engine of discovery. When data from a collision does not match the expected model, it is not a moment of defeat but of intense curiosity. A discrepancy is a whisper from the universe, a hint that there is something new to learn, a force or a particle or a principle that operates under conditions we have not yet fully reproduced. This mindset is absolutely essential when probing the very edges of reality, where the familiar rules of space and time dissolve. To study the Planck epoch or the nature of the singularity is to stand at the shore of a vast ocean of ignorance, and instead of turning away, to feel compelled to build a better boat. This scientific temperament, this comfort with not knowing, holds a profound lesson that extends far beyond the laboratory. In our daily lives, we are often pressured to have immediate answers, to project certainty in the face of complex challenges. Yet the most resilient and adaptable individuals and societies are often those that can cultivate a similar curiosity-driven stance. They see a complex problem not as a threat to be avoided, but as a puzzle to be engaged with, understanding that solutions may be iterative and that learning itself is the continuous goal. The story of recreating the early universe, then, is more than a chronicle of technological triumph. It is a masterclass in the human spirit's relationship with mystery. It demonstrates the incredible progress that becomes possible when we dare to ask enormous questions, not because we are sure we can answer them, but because the act of asking expands the boundaries of what we can conceive. It teaches us that the journey into the unknown, fueled by humble curiosity, is often more valuable than any fixed destination. In learning to listen to the echoes of creation, we are also learning how to learn, reminding ourselves that the universe's greatest gift may be its endless capacity to inspire wonder. These analogies are not mere simplifications, they are vital bridges across a chasm of scale. How do you describe a temperature of trillions of degrees or a time span of a yoctosecond to a human mind evolved to perceive a world of moderate climates and passing seasons? You cannot, so you reach for the familiar. You compare the universe's explosive growth during inflation to a loaf of raisin bread baking in an oven. As the dough rises, every raisin moves away from every other raisin, not because the raisins are traveling, but because the space between them is stretching. A raisin near the edge does not rush to get away from one in the center. The dough itself carries them apart. This simple kitchen image captures the core truth of cosmic expansion, that space itself is the actor, not the galaxies within it. It transforms an abstract, multi-dimensional concept into a tangible, sensory experience you can almost smell. Similarly, the Quark-Gluon Plasma becomes a primordial soup, a seething broth of the universe's most basic ingredients before they cooled and clumped into the solid chunks of protons and neutrons. We instinctively understand a soup, a unified medium where individual components lose their identity to the collective whole. The metaphor works because it conveys the fluidity, the homogeneity, and the transitional state of that early matter. Of course, the universe is not actually dough, and the plasma is not chicken broth. The analogies break down if pushed too far. Bread does not expand faster than light, and soup is not a perfect liquid with zero viscosity. Their power lies not in perfect accuracy, but in strategic imprecision. They provide a conceptual foothold, a first step onto the ladder of understanding. A skilled science communicator knows which detail of the metaphor to highlight and where to gently remind the audience that the reality is even stranger. This translation work is itself a creative and critical discipline. It requires deep empathy and understanding of both the complex physics and the lived experience of the listener. The goal is to craft a narrative scaffold strong enough to support the weight of the real theory, allowing the audience to climb high enough to glimpse the breathtaking vista of the actual science. When it works, a well-chosen metaphor does more than explain. It evokes a feeling. It allows someone to sense the grandeur of inflation or the bizarre perfection of that primordial fluid in their bones. It turns data into story and theory into a shared mental image, forging a communal moment of wonder where the unimaginable becomes, just for a moment, vividly real. This timeline of discovery is not a straight line, but a web of brilliant guesses, patient testing, and occasional happy accidents. It begins not with a particle collision, but with a persistent, annoying hiss. In the mid-1960s, two radio astronomers, Arno Penzias and Robert Wilson, were trying to calibrate a giant horn antenna in New Jersey. No matter where they pointed it, they could not eliminate a faint, uniform microwave static that seemed to come from all directions at once. They checked for pigeon droppings in the antenna, recalibrated their instruments, but the hiss remained. This cosmic noise, which they initially saw as a frustrating glitch, was in fact the cooled afterglow of the Big Bang itself, the cosmic microwave background radiation. Its discovery was the first direct, tangible evidence that our universe had a hot, dense beginning, transforming cosmology from theoretical speculation into an empirical science. It was the first major piece of the puzzle, proving the universe expanded from a singular, fiery state. With that starting point confirmed, theorists and experimentalists began working backward in time. To understand what happened before that light was set free, physicists needed a rulebook for the forces that would have been at play. This led to the development of quantum chromodynamics, or QCD, throughout the 1970s. This is the theory of the strong nuclear force, the powerful glue that binds quarks inside protons and neutrons. QCD made a stunning prediction that under conditions of extreme temperature and density, this binding force would weaken, allowing quarks and gluons to roam freely in a new state of matter, the Quark-Gluon Plasma. For decades, this plasma was a compelling mathematical idea, a theoretical specter from the universe's first microsecond. No one knew if it could ever be made real, or if it would behave as the equations suggested. The first major attempt to find it began at the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory in the United States. Starting in the year 2000, scientists there began smashing gold nuclei together at incredible speeds. The early data was a shock. Instead of the hot gas many expected, the particles streaming from the collisions showed clear collective flow, the signature of a liquid. By 2005, the RHIC collaborations announced they had created a new state of matter that behaved like a nearly perfect liquid, with properties consistent with the long-sought Quark-Gluon Plasma. It was a monumental validation, proving that this primordial substance was not just a fantasy, but a reproducible reality. The universe's first structured matter had been reborn in a Long Island laboratory. This work set the stage for the next giant leap at the Large Hadron Collider in Europe. With its far greater energy, the LHC could create Quark-Gluon Plasma at temperatures even higher than those achieved at RHIC, producing hotter, larger, and longer-lived droplets of the primordial fire. Experiments like ALICE, ATLAS, and CMS began a new era of precision measurement in the 2010s. They mapped the plasma's properties in exquisite detail, confirming its near-zero viscosity and studying its transition back into ordinary matter. Each new run of the collider provided terabytes of data, allowing scientists to compare their observations with supercomputer simulations based on QCD, refining our picture of the early cosmos with every analysis. This historical arc, from a mysterious hiss in a radio antenna to the controlled creation of the universe's first liquid, embodies the true spirit of scientific progress. It is a story of prediction and verification, where a theoretical framework like quantum chromodynamics guided engineers to build machines capable of testing its most extreme consequences. Each generation of researchers built upon the tools and insights of the last, whether it was the antenna technology of radio astronomy or the accelerator physics pioneered in earlier colliders. The timeline shows science not as a series of isolated eureka moments, but as a slow, collaborative climb, a cumulative process of asking better questions and building better tools to hear the universe's answers. Knowing this history makes our current explorations all the more meaningful, for they are the latest chapter in a grand, ongoing human endeavor to read our own origin story, written in the language of the cosmos. These frontiers of speculation are where the known physics of our recreations brushes against the profound unknown. While we have successfully brought the Quark-Gluon Plasma back to life, its full story is still being written. Physicists now aim to use these collisions as a microscope, searching for signatures of even more exotic phases of matter that might have existed fleetingly within that primordial soup. Could there have been a brief moment when the quarks themselves aligned, creating a superconductor that allowed electric currents to flow without resistance in the infant cosmos? Or perhaps, under certain conditions, the plasma organized into crystalline patterns, a fleeting solid state within the liquid fire. These hypothetical states are not science fiction. They are rigorous predictions from the equations of quantum chromodynamics, waiting for a specific, telltale pattern in the particle debris to confirm their reality. Finding them would add entirely new chapters to the thermal history of the universe, revealing a first microsecond even more complex and structured than we currently dare to suppose. At the heart of this lies a pivotal mystery, the precise nature of the transition itself. Did the universe cool from a quark-gluon plasma into protons and neutrons smoothly, like water turning to ice? Or was it a sudden, dramatic shift, a cosmic tipping point where the properties of matter changed abruptly? This is not a minor technical detail. The character of this phase transition is intimately tied to the fate of the matter-antimatter asymmetry. A sudden, violent change could have created shockwaves and defects in the fabric of spacetime, potentially amplifying any tiny initial preference for matter. A smoother transition might have suppressed it, by tuning our collisions, creating fireballs of different sizes and temperatures. We are essentially running the experiment over and over with different settings, watching how the freeze-out occurs. The goal is to map the cosmic phase diagram with the same precision a chemist maps the states of water, pinpointing the exact conditions where one form of reality gives way to another. This map is a direct line to understanding the single most important accident in history, the one that left behind a material world. The ultimate hope, however, is that these extreme conditions will reveal cracks in our current rulebook. The Standard Model is brilliant, but it is silent on the universe's biggest mysteries like dark matter and dark energy. Could it be that the particles or forces that make up dark matter were once active participants in the Quark-Gluon Plasma, influencing its flow and evolution? If so, their ghostly signature might still be imprinted in the collective motion of the particles we see today. Our detectors are now fine-tuned to look for any anomaly, any deviation from the predicted flow patterns that cannot be explained by the quarks and gluons we know. Such a discrepancy would be a beacon pointing toward physics that operates only at energies so high they have not been seen since the universe's birth. We are using the early universe as a filter, hoping it will catch something new that our tranquil, modern cosmos has allowed to fade from view. Some of the most mind-expanding speculations reach even further. The incredible energy densities we recreate are a stepping stone toward understanding the inflationary epoch that preceded them. Could the mechanisms that drove that exponential stretching of space leave any imprint on the Quark-Gluon Plasma that filled the universe immediately after? It is a long shot, but it connects the largest-scale mystery of cosmology directly to our laboratory experiments. Furthermore, theories that attempt to explain dark energy or the multiverse often involve new fields or dimensions that would have been activated in the extreme heat of the beginning. While evidence for such ideas remains highly speculative, the search itself is transformative. It forces us to ask the most fundamental questions about the nature of reality, questions that our current experiments may not answer, but which they uniquely equip the next generation to ask with sharper tools and clearer vision. This forward-looking perspective is what keeps the field vibrantly alive. Every data run, every system upgrade, is conducted with the quiet hope that today's routine measurement might contain tomorrow's revolutionary insight. The work is a blend of meticulous engineering and boundless imagination, grounded in the solid reality of steel and silicon, yet forever reaching toward the first spark of existence. It acknowledges that the most important discovery might be the one we have not yet conceived, waiting in the noise of a billion collisions, ready to redefine our place in the cosmic story. Our ability to recreate the dawn of time stands as a testament to something extraordinary within us. It reveals that we are not merely passive observers of a distant cosmic history, but active participants in its unfolding narrative. The first microseconds, once a blank page in the story of everything, have become a vibrant laboratory. In that laboratory, the theoretical predictions of a perfect liquid universe meet the hard data streaming from detectors buried deep beneath the ground. We have built bridges of steel and silicon back to a moment before stars, using the collision of lead nuclei to illuminate the Quark-Gluon Plasma, that searing primordial soup from which all structure emerged. This is not magic, it is the culmination of human curiosity forged into engineering, of imagination tested by mathematics. We took the faint whisper of the cosmic microwave background and asked it to speak louder, then built machines to answer back in the language of the early universe itself. The journey from a mysterious hiss in a radio antenna to the controlled creation of the cosmos's first matter is one of our species' greatest epics. It ties the immense gravitational seeds of galaxies directly to the quantum jitter of particles smaller than we can see, proving that the macrocosm and the microcosm are written in the same fundamental script. Every time a droplet of that primordial fire flashes into existence inside the Large Hadron Collider, we are doing more than confirming a theory. We are touching the bedrock of reality, learning the rules that allowed a universe of possibility to condense into a world that can wonder about itself. This transforms our relationship with the night sky. The stars are no longer just points of light. They are the descendants of a specific, testable set of conditions from the first microsecond. Their very existence is a puzzle we are learning to solve, piece by subatomic piece, here on Earth. Let that knowledge fill you with a quiet awe. The next time you look up, remember that the story of those distant suns begins in a state of matter we can now hold, however briefly, in our own hands. Their origins are not locked away in an unreachable past. They are being actively explored, questioned, and understood. This ongoing saga of cosmic discovery belongs to all of us. We would love to hear what part of this journey resonated most with you. Share your thoughts in the comments below, and if you want to continue exploring the universe's deepest mysteries, subscribe to join us for the next chapter.